Hey everyone, welcome to this week's topics for the finite element analysis. So this week we are going to look at the axisymmetric analysis related to the pressure vessel. We're going to consider a 3D solid model and also compare the analysis with the 2D surface model by setting up the boundary conditions. And also we will be comparing these numbers with the theoretical calculations for the stresses in the pressure vessel. The other topics for this week include the frequency analysis. So we're going to take a look at how the frequencies, the natural fundamental frequencies of the component can be found out. And the other topic that we will take a look at will be the static contact analysis, how to define the contacts. We've gone through this contact analysis a little bit, but we'll take a look at another example to define the assembly and then define the contacts and then perform the static contact analysis. All right, so let's begin with the first topic, which is the axisymmetric analysis. And as the name suggests, the axisymmetry is a critical factor in the analysis of these kinds of problems. Let's take a look at very briefly the differences between the thin pressure vessel and the thick pressure vessel. I'm sure those who are in the machine design class must have gone over this in quite details, but for those who haven't, this is just a brief outline and the overview of what kind of pressure vessel that we are calculating the stresses for. Okay, and so now let's take a look at this figure here on the right. So we can see the pressure vessel, the outside diameter, and the outside diameter is d plus 2 times t, and the inside diameter is d, and the thickness of this pressure vessel, or the thickness of the wall, is equal to t. So how we distinguish between a thin pressure vessel and a thick pressure vessel is that if we take the ratio of t over d, looking at these dimensions, and if the ratio is less or equal to 1 over 20, which means it's 0.05, then the classification is the thin pressure vessel. And for the thick pressure vessels, the ratio of t over d is greater than 0.05. Basically that's what it's used in defining the shell mesh, if it's a thin mesh or the thick mesh, based on this ratio of 0.05. Okay, so the other thing is that stress distribution in the thin pressure vessels is uniform throughout its thickness, because the fact that the the thickness is very small number, and so the stress distribution is quite uniform, but not necessarily in the thick pressure vessel, because the thickness is much more larger than the thin pressure vessels. So the stress distribution is not uniform here throughout the thickness. And the other important difference between the thin and the thick pressure vessel is that in thin pressure vessels, it can only handle or sustain the pressures from inside. Okay. However, the thick pressure vessels can sustain the pressure from both outside as well as inside, because obviously the fact that the wall is very thick. All right, so for the analysis of the problem, to set up the axisymmetric analysis, obviously there is a axis of symmetry, as you can see for this pressure vessel on the left hand side of this figure. And if I consider only 1/4 in the positive x positive y plane of the cross section of this pressure vessel, and if I consider only 1/4 of that cross section in the positive xy axis and redraw it here with the dimensions as shown, that is basically the problem we will be looking at to analyze. Because of the fact that it is symmetrical with respect to both the y-axis as well as the x-axis, that is why we can take the 1/4 of that, the complete cross section. We don't really need to analyze it, and by defining the suitable boundary conditions, we can get the stress distribution along the thickness of this pressure vessel that we can replicate for the other quadrants as well. So you can see that it is having 25 millimeters thickness, 100 millimeters outer diameter, 75 millimeters is the inner diameter. So that is the 75 times 2. I'm sorry, what I meant to say was 75 millimeters is the radius, okay, because this is the half, with respect to the y-axis. So 75 millimeter is the radius, and 100 millimeters is the outer radius. So 200 millimeters is the outside diameter, and 150 millimeters is the inner diameter. Okay, and so the total length is 400 millimeters, but half of that with respect to the x-axis is the 200 millimeters. So when we look at the T over D ratio and want to verify if it is less or equal to 1 over 20, we can see that T is 25 thickness and 150 is the 2 times 75 the inner diameter, and that ratio is 1/6 or 0.1667, and obviously that is greater than 0.05. So we can classify this type of a problem in a thick pressure vessel category. Okay, and the stresses that we will be looking at from the SOLIDWORKS we can compare with the theoretical calculations based on the thick wall pressure vessel cylinders. Alright, so let's go ahead and create this geometry in the SOLIDWORKS. Like I said in the beginning, we are going to be looking at the 3-dimensional as well as the 2-dimensional models for the analysis. Alright, so before we get into the SOLIDWORKS, first take a look at what kind of stresses those are important for this type of analysis. So in order to look at different types of stresses, if you search the stresses in thick cylinder in the Google, and then you click on the first link, which is from the engineering toolbox, the stress in thick wall cylinders or tubes. So if I click on that, that is the pressure vessel or a thick wall tube or a thick wall cylinder we are looking at. And so there are 3 important stresses that we want to look at. One is the axial stress, which is along the axis of the pressure vessel. Then you have the circumferential stress, sigma c. It's also called as the hoop stress. And on the other view, when we look at it from the front view, we can see that the circumferential stress in the vertical direction and the horizontal direction is the radial stress, right? So this along the radius of the tube or the cylinder. All right, so these are the 3 stresses which are important to calculate for the pressure vessels: the radial stress, the circumferential stress, and the axial stress. So these 3 stresses in 3 different directions, x, y, and z, we are going to look at in the SOLIDWORKS and then compare that with the theoretical calculations here. The equations for the axial stresses are given here, as well as the circumferential directions or the hoop stress, and also the stress in the radial direction. So the equations are given here for the thick wall cylinder, and obviously the stresses depend on the how much is the internal pressure, how much is the external pressure, what is the outside radius, the inner radius, RO and RI. So it all depends on these numbers. And they have this applet here. If we just plug in the values, we can calculate what are these stress levels. So for example, let's say in our problem we are going to use the 35 megapascal as the inside pressure. Let's not worry about the outside pressure too much. Let's say there is no significant amount of outside pressure. The inside radius we're going to find out at the inside radius point, which is 75 millimeters. Okay, basically you can look at it from this geometry here. So that's the 75. So we're going to look at these stresses at this point basically, which is at 75 millimeters from the vertical axis of symmetry. and the outside radius is 100 millimeters, and radius to the point where we want to find out the value is, let's say, 75 millimeters, radius to the point in the wall, which means that we're going to be looking at the values of the stresses at this particular point, which is 75 millimeters from the axis of symmetry. Okay, and obviously the outside radius is 100 millimeters. So once we use these values here and try to calculate, we get the values of the axial stress at that point is 45 megapascals, circumferential or the hoop stress is 125 megapascal, and the radial stress is negative 35 megapascal. So we're going to come back and look at these values and verify it in the SOLIDWORKS simulation. These are the three stresses in three mutually perpendicular directions, x, y, and z, depending on how the orientation of the the cylinder that we keep in the problem. We will have to define accordingly the axial, circumferential, and the radial stresses. All right, so let's go ahead and start with the SOLIDWORKS, and let's create a new part. Let's keep the units as millimeters, and let us create the quarter of that cross section. So I'm going to create that in the positive XY axis. So first I'm going to create this vertical line here and make that at 100 millimeters. Also, I'm going to keep them horizontal along the same line, and the overall height is 200 millimeters, the half of it. Then let's create the wall thickness of 25 millimeters, and then up to here. This is also 25. And then complete it. And also we can add this radius here, which is 25 millimeters at this location. Click OK. And so that's basically the quarter cross section of the complete cross section of the pressure vessel. And so there are two ways now to go about it. First thing is that we're going to make a 3D solid model of it, and then next we're going to take a look at the surface body model. Okay, so what I'm going to do is first take a look at the 3D model. So I will revolve this with the axis of revolution right there, and let's revolve it by 90 degrees. I'm going to take it to the other side. Alright, so that's the revolving the cross section by 90 degrees. And again, even if we consider a solid model, we don't really need to consider a complete 360 degrees revolved body. We can just simply revolve it by some angle and then define the boundary conditions accordingly, so that we can analyze that particular component. Alright, so let's click OK, and that's the solid model that we have. Now I'm going to take it to the simulation. Static study, click OK. First thing I'm going to do is apply the material. Let's use the plain carbon steel. And in terms of the fixtures, I'm going to use the roller slider support. So if I click on the roller slider support, I'm going to click on this face, the other face, which is supposed to be in continuation with the whole cylinder, and also the bottom face. So whichever the faces are, those are supposed to be in continuation with the continuous solid bodies. I have selected these three faces as the roller slider boundary conditions, and then click on the check mark. All right, the next thing I'm going to do is apply the pressure. So I'm going to right click on the external loads, go to the pressures, take a look at the megapascals. 35 megapascals is the value we want to put it in, normal to these three faces. That's the internal pressure of 35 megapascal. And click on the check mark. All right, and then you can refine the mesh, obviously around the edges where you can see that there will be higher concentration of the stress. But at this point, let me just run this simulation study with the default mesh. So I'm just going to go to create mesh, and then I will just simply run this study. Okay, and so this is what the result that we get, that there is a lot of pressure acting on the vertical direction here. And so now if I align it using Control+1 keys on my keyboard so that I can see this view from the front view orientation, what I want to do first is that I want to create the stress plot. So I'm going to go with the define stress plot in order to verify the values. I'm going to create these three stress plots, the X normal, Y normal, and the Z normal. Starting off with the X normal, let's use the units of megapascal. Click OK. And I'm going to repeat this procedure 2 more times, where I'm going to use first the Y-axis and then complete this with the Z-axis. All right, so I have these three stresses along the three normal directions, and so I'm going to start off, let's say, along the x-axis. If you look at this triad here, so this is the xy plane. So y-axis, it looks like it's the axial stress, and x-axis looks like it's the radial stress. So first I'm going to take a look at the x-axis, and along the x-axis I am going to probe the value for the x-axis at the location where we said we're going to look at it at the 75 millimeters from the axis of symmetry, and this value appears as negative 34.8 megapascals. So let's go back to the theoretical verification and see if that's the negative 34.8 or basically negative 35 megapascal. So that compares really well with the radial stress value. So along the x-axis direction, that is the radial stress value of 35 megapascals, which is confirmed. Along the y-axis, as you can see, if we want to find out, that's basically the axial stress. So I'm going to double click on the y-axis, and then again, if I probe it and take a look at the value for the radial stress, which is 46.6 megapascal, and again let's go back to verify this value. So the axial stress is about 45 megapascal, and again that compares really well with the 46.6 megapascal, the value that we obtained. And then finally the comparison or the validation with the z-axis, which is the circumferential stress direction. Probe, click there, and we get 128.2 megapascal. So looking at this calculations, 125 megapascals for circumferential or the hoop stress. All right, so that's basically in a very good agreement with the theoretical values that we have got from the SOLIDWORKS results. Okay, so you don't really need to analyze a complete 360 degrees model if you just use these boundary conditions as what we used here for these three faces. You can still calculate the stresses which are in really good agreement with the theoretical values. All right, so that's the solid model. Let's take a look at the surface body model now. So I'm going to go back to the model, and let's take a look at the simulation study. And this time I'm going to use the 2D simplification. So if I use the 2D simplification and click on the check mark, remember we have been doing the plane stress for some of the previous surface body problems. This time I'm going to use axisymmetric model. Okay, so we can use a 2D surface body for the axisymmetric condition. So it's going to ask you what section plane that we want to use. So I'm going to use this particular section plane and the axis of symmetry, which is this line, right? So that's how we can define this problem for the axis of symmetry and this section. So essentially what it means is that along this axis we are revolving this the surface body to make it a axisymmetric body problem. Click OK. And we're gonna have to do pretty much the same thing as what we did for a three-dimensional analysis problem. So starting off with the part material, I'm going to use the plain carbon steel, and for the fixture again I'm going to use the roller slider for this edge and the other edge, the horizontal edge. So only the edges which are supposed to be in continuation with the otherwise continuous body for this analysis. So that's that, and then click OK. External loads, let's use the pressure. I'm going to change the units to megapascal, 35 megapascals, and use these three edges so that the pressure is acting normal, and then click OK. And once we do that, that's pretty much defines the problem setup, define the material, boundary condition, and the force, or sorry, the pressure. And then I'm going to use mesh and run. And again, similarly, we are going to create the different types of stress plots. So starting off with the x axis, and then y, and then z, to validate these values with the theoretical calculations. And hopefully we'll get the same values, but the idea is that we are saving large amount of the computational resources in terms of the mesh statistics, as we can also compare after we validate these results. Okay, so let's again put it control and 1 to align it as the horizontal, in the front plane. I'm going to go to the x-axis, which is basically the radial stress, and I'm going to probe it right there. So again, it's negative 34.99. So we looked at it before. For the radial stress, the value was negative 35. Yeah, and so that is the correct answer. Again, for the y-axis, if I probe it, should be close to 45, so it's showing 46.2 megapascal, so that is also correct. And then z-axis was somewhere close to 125 megapascal, and so this is coming out to be 127.4 megapascal. So that's also in a fairly good agreement with the theoretical value as well as with the solid model value. So if you look at the mesh statistics, here we are using close to 5,000 elements and 10,000 nodes, and for this problem we used 7,000 elements and 11,000 nodes. So it's not a really large number of saving in terms of the mesh size, but again there is at least some advantage of dealing with the simpler geometry, so that you still get the accurate results as compared to three-dimensional or a two-dimensional model to validate with the theoretical values. Alright, so one last thing before we close on this particular topic is that you can always if you want to probe the results at particular nodal location, what you need to do is, let's say you want to take a look at these stresses at particular locations. So when let's say we double click on the particular plot, and if I want to probe this, so sometimes I don't really know where I'm clicking here, I cannot really see what nodes that I'm clicking on. So if you want to probe the value at particular nodal point, what you need to do is right click on the edit definition. Under the settings, for the boundary options, what we can do is we can use the mesh option here. So the mesh will be embedded on the solid model, and so that way once we do that, then if we go to probe, then we can get the exact values at whatever the nodal locations we want. Okay, so that's the idea of taking the measurements at particular nodal points. You can also go to evaluate, you can go to measure, and you can click on particular nodes, right? So it also gives you some other information as well about the nodal points. Alright, so that's it for this particular video over the axisymmetric analysis, and I'll see you in the next video for the next topic.